Chapter 13 is an introduction to software for managers. Managers who understand software are in better position to understand the technology needs of their organizations and can make better decisions regarding the strategic value of IT and the potential for technology-driven savings. This chapter introduces students to basic computing concepts and describes the different types of programming languages and ends with a discussion on the different categories of costs associated with an organization's information systems and the reasons for technology failure. Although the advancements in computing hardware are creating exciting opportunities, it is software that makes the magic of computing happen. Managers who understand software can better understand the possibilities and impact of technology. If a computer system can be equated to a layered cake, from bottom to top order, the layers are hardware, operating systems, applications, and users. This is shown in Figure 13.1. The flexibility of these layers gives computers the customization options that managers and businesses demand. The physical components of information technology are referred to as hardware. A video game console is an example of computer hardware. The next two layers, applications and operating systems, are both classified as software, the focus of this chapter. Software refers to a computer program or collection of programs, sets of instructions that tell the hardware what to do. The operating system is a collection of programs that control the hardware. For example, Linux is an operating system that is open sourced. In other words, it was developed for anyone to freely use. Android is a software product developed by Google that allows cell phone manufacturers to control hardware and establishes standards for developing and executing applications on its platform. Android is thus an example of an operating system. Microsoft's Xbox operating system provides Xbox programmers with a set of common standards to use to access controllers, the Kinect motion sensor, play sounds, draw graphics, save files, and more. Without this, games would cost more. Applications range from end-user programs to the complex set of programs that manage a business's inventory, payroll, and accounting. Microsoft Word is an example of application software. It is software applied to the problem domain of word processing. Operating systems control the hardware, while application software performs the work that users and firms are directly interested in accomplishing. Applications can be thought of as places where a user's real work is done. Understanding how these layers relate to each other has managerial implications in many areas, including the flexibility in meeting business demand, costs, legal issues, and security. For example, compliance refers to the practice of ensuring that an organization's systems operate within required legal constraints and organizational obligations. An operating system provides a common set of controls for managing computer hardware, making it easier for users to interact with computers, and also for programmers to write application software. Some firms develop their own proprietary operating system, while others buy operating systems from vendors like Microsoft. Same applications may look and behave differently in different operating systems. Graphical user interface, or GUI items like scroll bars and menus, are displayed on the hardware of the computer display. Most operating systems also include control panels, desktop file management, and other support programs to work directly with hardware elements like storage devices, displays, printers, and networking equipment. Operating systems are also designed to give programmers a common set of commands to consistently interact with the hardware. These commands reduce program complexity and make it faster to write software while minimizing the possibility of errors in code. A good operating system and software development platform can catalyze network effects. Firmware refers to control software stored on non-volatile memory chips. Many smaller, special-purpose computing devices have their operating systems installed on read-only memory or ROM chips. Control programs stored on chips are referred to as firmware. Special-purpose software designed and included inside physical products are referred to as embedded systems. Software, often firmware, designed to make physical products and devices smarter by doing things like sharing usage information, helping diagnose problems, indicating maintenance schedules, Providing alerts or enabling devices to take orders from other systems is referred to as embedded systems. Moore's law enables embedded systems, and these systems can create real strategic value. Embedded systems can make products and services more efficient, more reliable, more functional, and can enable entire new businesses and create or reinforce resources for competitive advantage. Operating systems are designed to create a platform so that programmers can write additional applications, allowing the computer to do even more useful things. While operating systems control the hardware, application software perform the work that users and firms are directly interested in accomplishing. Desktop software refers to applications installed on a personal computer, typically to support tasks performed by a single user. Enterprise software refers to applications that address the needs of multiple simultaneous users in an organization or work group. Inventory tracking is likely to be performed by enterprise software. Another term you might hear is apps. Most people use the term to refer to smaller pieces of software that are designed for a specific platform, such as the programs that execute on a smartphone, tablet, television, or specialized platform like the Apple Watch or Oculus Rift. Some companies buy a software package, a software product offered commercially by a third party, to support some of their functions. Enterprise Resource Planning, or ERP, refers to a software package that integrates the many functions of a business such as accounting, finance, inventory management, and human resources. An ERP system with multiple modules installed can touch many functions of the business such as sales, inventory, manufacturing, human resources, purchasing, order tracking, and decision support. ERP accomplishes this by a common database called a repository. Customer Relationship Management, or CRM systems, support customer-related sales and marketing activities. Supply Chain Management, or SCM systems, can help a firm manage aspects of its value chain, or the series of events involved in acquiring and converting raw materials into a sold product. Business Intelligence, or BI systems, use data created by other systems to provide reporting and analysis for organizational decision making. Most enterprise software works in conjunction with a database management system, or DBMS, which stores and retrieves the data that an application creates and uses. Firms that don't have common database systems with consistent formats across their enterprise often struggle to efficiently manage their value chain. Common procedures and data formats created by packaged ERP systems and other categories of enterprise software make it easier for firms to use software to coordinate programs between organizations. So database management systems are central to accomplishing supply chain management, for example, a web-based e-commerce website. As you can see from Figure 13.4, it is the organizational database that serves as the backbone technology for all other strategic applications in the firm. Many products, from hefty ERP systems to end-user application suites, are being delivered via the cloud. You'll also learn about additional classifications of software, including artificial intelligence and machine learning systems. These systems mimic or improve upon functions that would otherwise require human intelligence. Packaged enterprise systems can streamline processes, make data more usable, and ease the linking of systems with software across the firm and with key business partners. Packaged systems are often debugged, tested, and documented with an industrial rigor that may be difficult to match with proprietary software developed in-house. Standardizing software business processes that others can buy means that those functions are easy for competitors to match. There are some problems associated with enterprise solutions. Enterprise software installations have proven difficult. These functions are easy for competitors to match. Most of the installations are costly and failures could be disastrous. Companies that have efficient, flexible information systems don't just see value through operations efficiency and cost savings. Technology can also influence a firm's options with respect to inter-firm partnerships, as well as merging with, acquiring, or getting acquired by other firms. When computers in different locations can communicate with one another, this is often referred to as distributed computing. This can yield enormous efficiencies in speed, error reduction, and cost savings, and can create entirely new ways of doing business. Firms create platforms for several reasons. One, platforms can provide the potential to make their products and services more useful. Platforms can also widen the reach of firms and products. Third, they can create switching costs. And finally, platforms can enhance network effects. The term server is frequently used in two ways. In a hardware context, a server is a computer that has been configured to support requests from other computers. In a software context, a server is a program that fulfills requests. Many distributed computing services, including the World Wide Web, use client-server systems. It refers to two pieces of software, a client that makes a request and a server that receives and attempts to fulfill the request. More advanced distributed environments may use a category of software called an application server, which houses business logic for a distributed system. Individual software components or web services served up by the app server are programmed to perform different tasks, such as returning calculations, accessing database programs, and making requests to another server in another organization. The World Wide Web Consortium defines web services as software systems designed to support interoperable machine-to-machine interaction over a network. You might also hear the term API used to describe the same concept. Organizations that have created a robust set of web services around their processes and procedures are said to have a service-oriented architecture, or SOA. EDI, or Electronic Data Interchange, is a set of standards for exchanging messages containing formatted data between computer applications. The most common function performed by EDI is sending electronic equivalents of structured documents between different organizations. You can think of EDI as computer-to-computer email, where responses are programmed and do not require humans to read or otherwise work on the email. So it's automated computer-to-computer email. EDI is used in an environment where there are many transactions between organizations. And one driver of EDI is to reduce the need for paper. In EDI, each element in an electronic document is coded so that it can be recognized by the receiving computer program. JavaScript object notation and extensible markup language are technologies being used to replace the older EDI for specifying data standards. XML, or extensible markup language, allows software developers to create a set of standards for common data elements that can be sent between different kinds of computers, different applications, and different organizations. XML was initially the go-to technology for specifying the format of data exchanged in web services, but today's APIs are more likely to use an even more compact and simple standard known as JSON, or JSON. While the name JSON contains JavaScript, a popular programming language for client and server software development, the standard is now used in a host of languages beyond JavaScript. The benefits of connectivity come at a price of increased risk. When systems are more interconnected, opportunities for infiltration and abuse also increase. Programmers write software in a programming language which provides standards, syntax, statements, and instructions for writing computer software. Many commercial software are written in a variant of the C programming language, such as C++, C#, which is written C and the pound sign, or Objective-C, the original language used for Apple's iOS app development. Some programming languages are extended by frameworks, which are libraries, templates, and extensions that simplify and standardize common tasks, speeding software development, reducing errors, and prompting reuse. Most professional programmers use an integrated development environment, IDE, to write their code. The IDE includes a text editor, a debugger for sleuthing out errors, and other useful programming tools. The IDE will also compile a programmer's code, turning higher-level instructions to lower-level instructions. This process of converting a code into machine-readable form is known as compiling. Java, a programming language developed by Sun Microsystems, allows software to be written once and run everywhere. Special Java commands control the user interface or interact with the display of other hardware. Java programs can run on any computer that has a Java Virtual Machine, or JVM. Java is used in websites, animation, games, mobile phone applications, etc. Java is not optimized to take advantage of interface elements specific to the Mac or Windows operating systems. As a result, Java is unsuitable for desktop applications. Platform independence is said to be Java's biggest selling point. Scripting languages such as VBScript typically execute within an application. Scripting languages are interpreted within their applications rather than compiled to run directly by a microprocessor. Firms are well served to leverage established project planning and software development methodologies. The idea behind these methodologies is straightforward. Why reinvent the wheel when there is an opportunity to learn from and follow blueprints used by those who have executed successful efforts? Software development methodologies, sometimes referred to as the Software Development Lifecycle, or SDLC, are methods to divide tasks related to software creation and deployment into tasks targeted at building better products, having stronger product management guidelines and techniques. The waterfall method is the classic but increasingly out of favor approach for system development. It is a relatively linear sequential approach to software creation. Project progress flows largely in one direction, downwards, from one step to another like a waterfall, through phases often listed as requirements identification, design, implementation, verification, and maintenance. The use of upfront documentation can help prevent feature creep or expansion of the scope of the project. Agile development has become the dominant software development methodology. This method focuses on developing work continually and iteratively, with the goal of more frequent product rollouts and constant improvements across smaller components of the larger project. Components of the Scrum approach include roles, artifacts, and ceremonies. Scrum is an approach to organizing and managing agile projects. Scrum breaks projects into tasks called sprints that are meant to be completed in 1 to 6 weeks. Roles involve job functions. For example, a product owner who advocates the needs of the organization, helps in setting requirements, and is ultimately held accountable for deliverables. A Scrum Master is someone who serves the team by running meetings, keeping teams on process, and acting as a buffer to external team distractions. The team provides analysis, design, development, testing, documentation, and more. Artifacts are a way of documenting work in its current state. Things that need to be documented are the product vision, the product backlog, the sprint backlog, and the task board or burn down chart. Ceremonies are essentially meetings. Meetings may be classified as sprint planning, a team planning meeting where stories are fleshed out and the goal and scope is determined, or a daily scrum, a daily stand-up team meeting to discuss what is completed since the previous meeting. Another type of ceremony is the sprint demo and review of retrospective. In this case, the team demonstrates completed work to the product owner and discusses what worked and what can be improved for the next sprint. Different types of costs are associated with creating and supporting an organization's information systems. The costs include programming costs, licensing, design and documentation, and testing. Perhaps the most expensive part of system development is the final stage of maintaining it after it has been implemented. Firms need to constantly engage in a host of activities to support the system, which may also include providing training and end-user support, collecting and relaying comments for system improvements, auditing systems to ensure compliance, providing regular backup of critical data, planning for redundancy and disaster recovery in case of an outage, and vigilantly managing the moving target of computer security issues. These tasks are often collectively referred to as the total cost of ownership, or TCO, of an information system. An astonishing 1 in 3 technology development projects fail to be successfully deployed. Sometimes technology itself is to blame. Other times it's a failure to test systems adequately, and sometimes it's a breakdown of process and procedures used to set specifications and manage projects. Projects rarely fail for just one reason. Project postmortems often point to a combination of technical, project management, and business decision blunders. The most common factors include poor goal setting, including the lack of clarity or ability to achieve goals, weak project leadership and project management, non-existent or limited executive commitment, poorly forecast resource needs, and inadequate access to required resources, project complexity, as mentioned before, scope creep or changing the increasing requirements during project development, ineffective project reporting and poor communication across constituents that include the project customer, end users, developers, and others in firm and IS operations. Also, inappropriate technical choices, including immature technical offerings. Another common factor leading to technology failure is the inadequate testing and deployment procedures that should catch flaws before major rollout. In other words, not catching the problems early enough. Another factor is internal and external politics, squabbling, and misalignment of priorities among stakeholders. Finally, time and delivery pressures that encourage corner cutting, ethical lapses, or other design weaknesses. Mechanisms for quality improvement include Capability Maturity Model Integration, or CMMI, which gauge an organization's process maturity and capability in areas critical to technology projects, and provides a carefully chosen set of best practices and guidelines to assist quality and process improvement. Firms are also well served to leverage established project planning and software development methodologies that outline critical business processes and stages when executing large-scale software development projects. Your book provides a good example of project failure and repair. To say the Affordable Care Act was controversial is an understatement. Politics aside, technology had to work, and at rollout it didn't. The Affordable Care Act called for a website, healthcare.gov, that served as a national healthcare exchange where citizens could shop for, compare, and enroll in healthcare plans. The site would also offer subsidies for low-income enrollees and assist those eligible to sign up for Medicaid. Over 250,000 users visited healthcare.gov on day one, but total enrollment after the first day was 8 users because the system was so bug-ridden and design flawed. The most critical issue was lack of clear authority. Technologists were also not involved in top-level planning. The clear stages that most large-scale systems have, requirements definition, design, development, and testing phases, were started on top of one another, where design and development began before requirements definition was even complete. The agile software development methodologies used rely on regular testing of modules developed along the way, but there were no such precautions taken. Twitter's CTO, or Chief Technology Officer, and current Kleiner Perkins partner Mike Abbott was brought in to help fix the system and said that you never open a service like this to everyone at once, exactly what happened with healthcare.gov, but in small concentric circles and expand. The lack of testing also led to no credible verification on project status. Pre-deployment testing was minimal and non-existent, and the system was implemented in a single big bang rollout. At best, the site could tolerate 1,100 simultaneous users at launch, nowhere near the 50,000 to 60,000 expected or the 250,000 reported on the first day. Healthcare.gov lacked the most basic performance dashboard to measure the website's performance. The user experience was horrible, from increased wait times to being kicked off mid-enrollment. A team of seasoned technologists was brought in, including Todd Park, White House CTO, Jeff Zients, who had experience running large bureaucratic programs, Mickey Dickerson, Google's site reliability engineer, and Gabriel Burt, CTO at Civis Analytics. At times it seemed that bureaucracy was conspiring to halt goodwill. Government regulations don't allow for volunteers to work on government projects for sustained periods of time. New leadership actually had to be put on the payroll of contractor QSSI as hourly workers, earning Dickerson what he reported as a fraction of his Google pay. Clearly, priority setting, results reporting, and coordination were implemented through stand-up meetings, common among practitioners of agile development. As the name implies, stand-ups are meetings where technologists stand up, are quick to the point, identify a problem or set of problems, identify obstacles to gaining a solution, gain quick feedback from the group, then disperse to solve presented problems, reporting back at the end of the day to recap. After the projected 7 million enrollees figure was revised to 6 million after persistent glitches, Healthcare.gov had actually signed up over 8 million insurance users by mid-April, 2 weeks after the original deadline. This issue was not an anomaly. In the past 10 years, some 94% of large federal information technology projects were unsuccessful. That's the end of Chapter 13. Thank you.